Hi everyone. Today we're doing notes for 5.8 linear and quadratic patterns. A linear equation produces a straight line when you graph it. Each value of x produces one and only one value of y. When you graph a quadratic equation, you produce a parabola that begins at a single point called the vertex and extends upward or downward in the y direction. The relationship for any given value of y, except the y value of the vertex point, has two values for x. So you can see in the graph to the left, the linear equation is the red line, and the quadratic equation is the blue parabola. So here's our first example. In 1980, a brand new Mercedes with a 300 diesel engine cost $23,000. The price went up each year as seen in the following data table. So it says for question A, what is the explanatory variable? So in this case, this is going to be the years since 1980. Question B, what is the response variable? This is going to be our price in dollars. What patterns do you see in the collected data? So if we look at the price here, we go from 23,000 to 23,700. So that's an increase of 700. 23,700 to 24,400 again was an increase in 700. And if we keep looking at the numbers, we can see that every year we're increasing by $700. So the pattern we see is every year the price increases by $700. So then it says fill in the box with the number that continues the pattern. So if I add 700 to 26,500, that's going to give me 27,200. Are these linear related data, y or y not? So yes, because it's a constant increase of $700 each year. Write an equation for price as a function of years since 1980. So we have f of x equals, now our change of $700 per year, that's going to give us our slope. So we can say 700x plus our y-intercept is our starting value, which is the $23,000. What does the slope mean in the context of the problem? We would say for each year after 1980, the price increases by $700. Okay, let's go to the next page. Below is the data for money spent in the US on personal technology beginning in 1970. What is the explanatory variable? So this is going to be our years since 1970. What is the response variable? This will be billions of dollars. What pattern do you see in the collected data? All right, so let's check. From 1 to 1.5, that's an increase of 0.5. From 1.5 to 3, that's an increase of 1.5. 3 to 5.5 is an increase of 2.5. 5.5 to 9 is an increase of 3.5. 9 to 13.5 is an increase of 4.5. So what's happening, if we notice, each of these increases is increasing by 1. Okay, so we could say the pattern we see is that the increase is increasing by 1 billion each time. All right, so are these linearly related data? Why or why not? No, they are not, because it's not a constant increase. And that applies for decreases too, so I'll put change in parentheses. So again, it's not a constant change that's happening. All right, so we need to plot our data here. So our years since 1970, we have 0 through 6. That's going to go on our x-axis. And then our y-axis, the billions of dollars, we're going to start counting up from 0 also. All right, and I'm going to add some labels for us. Our x-axis, again, this is our years since 1970. Our y-axis, this is the billions of dollars. All right, so we have the point 0, 1. Then we have 1, 1.5. We have the point 2, 3. We have the point 3, 5.5. We have the point 4, 9. 5 is at 13.5. All right, so we have a curve here. And then it says fill in the box with the number that continues the pattern. So if we're going to increase by 1 again, this is going to be an increase of 5.5. So that last value is going to be 19 to finish the pattern. And then it asks what type of graph is plotted, and this is a quadratic. In this case, we have just the right half of our parabola. All right. The article, Masters Performance in the New York City Marathon, gave the following data on the average finishing time by age group for female participants in the New York Marathon. What is the explanatory variable? So here we have age. What is the response variable? And this is the marathon finish time. Using representative age and average finish time, plot the data using technology and sketch the graph. So let's take a look at this. And so we're going to make a table. And so we have our representative age is going to be our x values. So we have 15, then 25, 35, 45, 55, and 65. Then for the average finish times, we have 302.58, 193.63, 185.46, 198.49 224.30 and 288.71. All right, so then we'll click on the magnifying glass so we can see our data here. And I think we're going to need to spread this out a little bit more. Oops, I'm missing a decimal point. There you go. Let's try again with the magnifying glass. There we go. And so now if we're looking at the data, if we're trying to decide if this looks more linear or more quadratic, this definitely looks like a parabola. So let's fill that in. And we're going to draw a sketch. So we saw a point up here. It looks kind of like this. And it is quadratic looking. Then we have to find the regression equation. So when we do this, it's similar to linear regression. You're going to do y1 tilde ax1 squared plus bx1 plus c. So again, that's what we're going to enter into Desmos. So let's go do that. So again, y1, then our tilde, and then we have ax1 squared plus bx1 plus c. And so again, just like a quadratic looks like ax squared plus bx plus c, we're putting in that same format, and we have our y1 to get our y data from the table, and we're using x1 twice to get our x data from the table. And so we can see that quadratic regression fits our data pretty closely. All right, so our A, if we round to 3 decimal places, we get 0.179. Our B is negative 14.223. And our C is 462.383. So let's write these down. All right, so again, we had y hat, because it's the predicted line, equals, it was 0.179 x squared plus a negative 14.223 x plus 462.383. All right, our next question asks, which of the following are quadratic functions? And so quadratic function, remember, is anything where we have the x squared in it. So we have A is a quadratic function, B is a quadratic function, C, we do have 2x squared, but we also have this x to the 1.2 power. And remember, quadratic functions are where it looks like ax squared plus bx plus c. And so we can't have the 1.2 as the exponent, so c is not the quadratic function. Okay, our last example says for f of x equals negative x squared plus 2x minus 1 and g of x equals negative 3x plus 10, find the following. Remember to first put parentheses around each variable when you substitute values for the variables. So first we have g of negative 3. So if I plug this in, this is going to give us negative 3 times negative 3 plus 10. Well, negative 3 times negative 3 is 9, plus 10 is 19. Next we have f of 2. So I have negative times 2 squared plus 2 times 2 minus 1. 2 squared is 4 times the negative is negative 4. 2 times 2 is plus 4 minus 1. Negative 4 plus 4 is 0. Minus 1 is negative 1. And last, we have f of negative 3. So this is negative of negative 3 squared plus 2 times negative 3 minus 1. Well, negative 3 squared is 9 times the negative is negative 9. 2 times negative 3 is plus, we have negative 6 minus 1. So negative 9 plus negative 6 is negative 15. Minus 1 is negative 16. And that is the end of our notes for today.